Now we're going to move into a completely different way of solving some of these problems. So in the previous section, what we did was we established an instantaneous relationship between the forces and accelerations and then integrated as needed to find position and velocity. So by this, I mean we knew what the acceleration was for any moment in time. We knew then we could find out the velocity and the position for any moment of time. But there's certain problems where we don't need to know what those values are for every moment in time. We're looking at the cumulative effects, and then we just look at very particular moments in time. So a super basic example would be, let's say you had sort of a table here, and you have a block on the table, and this would be your position 1, and then you have the block on the ground, and this is your position 2. And so maybe you don't care what happens between the block falling off the table. You just care what's happening before the block when it's on the table, and then you care what's happening with the block on the ground. And so when we're doing work energy methods, we have to identify specific moments in time, and we just analyze what's happening at each moment. Whereas in the previous section, we were looking at that instantaneous relationship. So we had something like V of t is equal to t squared, for example. Here, I can figure out the velocity for any moment in time. In this section, I'm just going to know what's happening, at this moment, Maybe I could add one more moment in the middle here if I was interested in that. So it's a different way of solving these problems, but sometimes it can make the solving a little bit easier. There's actually 2 ways that we do this. The first way is an integration of forces with respect to displacement. And we'll get into the specifics of that in a second, but that's this video. So this is the work energy methods. And then we also have integration of forces with respect to time. And these are the equations of impulse and momentum that we'll get into in the next chapter. So what we do is we incorporate the results of these integrations, and the real benefit to us is that it becomes unnecessary to solve for accelerations. So in the case of the work energy methods, we can actually relate the forces, the mass, the velocity and displacement are related without considering acceleration. So in that case, it simplifies the problem. So I'm going to just move the screen up here. And I'm going to define a few terms. So first we need to define what displacement is. Displacement is the vector that connects a particle from its initial position to its next position. So let's say we had an origin here, and our particle was first up here at position A. The vector that connects the origin to the particle at the first position would be our vector r. But if A moves and A is over here now, so this would be position A prime of our particle, then we would have a position vector r prime that connects the new position. The differential between them, so the vector that connects the first position of the particle to the second position, this is your dr, and this is your displacement. So your displacement is the vector dr. Let's say it was a force that caused the motion. So let's say it was some force here, F, that caused that motion. And there were some restraints, which is why the directions don't line up. Then we can define the work of the force F corresponding to the displacement as du is equal to the force, oh sorry, this should be a vector here, the force scalar product with the displacement. So this is the work, this is the force, this is the displacement. And here we've got a dot product. And the reason for this is that it's only the component of the force that's in the same direction as the displacement that counts towards the work. Another way of writing out this dot product would be du is equal to F ds cos alpha. Now it's not super important to understand dot products and scalar products. You're actually going to do that a lot in your next course. And so I'll just do an example to show you what this actually means sort of in real life. So let's say we have a block here that's moving, it's on a table, and this is point 1, and then the block moves to point 2. Now let's say the difference between them is S, and we have a force here of F. Our force is in exactly the same direction as that displacement. So that means that all of the force is being used to move the block. So the work that's being done, the work U, is equal to the force times the displacement. You just multiply it. But let's say you have the same block here, still moving along the table, but this time the force is coming in at an angle. What we're saying here is that it's only the force that moves in the direction of motion that counts. So in this case, we only care about the component of the force that's along the path of motion. We can call this theta, and that would be equal to F cos theta, right? So then here we say U is equal to the force cos theta times that distance S. So it's only the component of the force that's going along the path of motion, the line of action, that counts. So that's why we take the cos alpha to figure out which component is moving in the same direction. Another note, I'm going to move this up just a little bit, is that it's only the line of action that counts. So let's say our block was initially on a slope here. Our block is here, and we have a force coming in at some angle here to push on the block. Now we have two angles, right? Because now we have this angle here, which I'll call beta, and then we also have this angle here that I'll call theta. In this case, the path of motion is along here because it's going to be moving up the bank. And so the angle that we're interested in is this angle here, theta. We don't have to worry about beta. So here we would still have U is equal to F cos theta times the distance S. So just to reiterate, work is equal to the force times the distance, but only the force along the line of action. Work is denoted as U. If we know the two positions, we would say work from position 1 to position 2 is equal to the integral from 1 to 2 of the force dot product dr, and we use the dot product here to indicate only along path of motion. And we have to integrate it because the force might change depending on the position. So that's why we have an integral, just in case it's changing. If the force is constant, you don't have to integrate. You just multiply them like we did in our examples above. Positive work is in the direction of positive motion. So you could have negative work. I'm going to move this up. Positive work is in direction of motion. negative work is opposing direction of motion. And work is a scalar, not a vector. Your distance s can be an odd path. So let's say you had you had a block traveling along some sort of odd path here. Your block was here and it moved over here. Your s would be the distance. S is the distance. I think I'm going to run out of time for the next section, so I'm going to do the rest of this in a new video.